Welcome to the Workshop Corrosion channel. My name is احتشام زاده. An introduction to this channel is available on video number E28. Chapter 3, Section 7, Types of Corrosion, Damage Mechanisms, Oxidation. The main reference, damage mechanisms affecting fixed equipment in the refining industry. API RP 571. Oxidation, description of damage. Oxygen, most often present as a component of air, approximately 21%, reacts with carbon steel and other alloys at high temperatures, converting the metal to oxide scale and thereby reducing the metal wall thickness. Internal oxidation, FeO, Fe3O4, Fe2O3. Oxidation products on iron. High temperatures, usually above 400 degrees Celsius, speed up the rusting process by increasing the kinetic energy of the particles involved, leading to more frequent collisions and a faster reaction rate. This is why iron objects rust faster in hot and humid environments compared to cooler, drier ones. Fe, FeO, Fe3O4, Fe2O3. Phase sequence. The most oxygen-rich compound, Fe2O3, is found at the scale gas interface, and the most metal-rich compound, FeO, at the metal scale interface. Above approximately 560 degrees Celsius, iron undergoes oxidation, resulting in a specific phase sequence. Fe, FeO, Fe3O4, Fe2O3, O2. Affected materials. A. All iron-based materials, including carbon steel and low-alloy steels, both cast and wrought, are affected. B. All 300 series stainless steel, 400 series stainless steel, and nickel-based alloys also oxidize to varying degrees, depending on composition and temperature. Critical factors. 1. The primary factors affecting high-temperature oxidation are metal temperature and alloy composition. 2. Oxidation of carbon steel begins to become significant above about 1000 degrees Fahrenheit. Rates of metal loss increase with increasing temperature. 3. In general, the resistance of carbon steel and other alloys is determined by the chromium content of the material. Increasing chromium levels produce a more protective oxide scale. Passive film formation in stainless steels. Stainless steel part free of contamination. The chromium content in the stainless steel reacts with oxygen in the ambient air. The chromium oxide layer is reformed and protects against corrosion. Cr2O3 protective layer. The 300 series stainless steel are resistant to scaling up to about 1500 degrees Fahrenheit. 4. The presence of water vapor can significantly accelerate oxidation rates of some steels, including 9 chromium 1 molybdenum. This figure shows enhanced oxidation of the 9% chromium steel P91 in water vapor containing environments. Mass change increases with increasing time in wet environment, remaining approximately constant in dry environment. Again, in water vapor containing environment, the mass change increases, and again, in dry, it remains approximately constant. This test is isothermal at 650 degrees Celsius. This table shows estimated oxidation rates in millimeters per year. Increasing temperature from 495 to 800 degrees Celsius. and this column shows the materials. The materials are carbon steel, 1¼ chromium, 2¼ chromium, 5 chromium, 7 chromium, 9 chromium, 12 chromium, 304 stainless steel, 309 stainless steel, 310 stainless steel, 800 H. As the percentage of chromium increases, the corrosion rate remains at a low value of 0.03 millimeters per year until higher temperatures. Estimated oxidation rates is 0.03 millimeters per year. This table shows estimated oxidation rates in MPY or mils per year. Again, increasing temperature in degrees Fahrenheit, increasing chromium, and in this triangle, the estimated oxidation rates are 1 MPY for all of these alloys. And this table shows estimated oxidation rates in millimeters per year when the temperatures are more higher, from 830 degrees Celsius to 1135 degrees Celsius. Again, increasing chromium. And this triangle shows the resistance alloys in these temperatures. Wherever data is missing, like here, here, it means that the alloy has a high corrosion rate and is not durable at that temperature. Carbon steel, 1¼ chromium, 2¼ chromium, 5 chromium, 7 chromium, 9 chromium, and 12 chromium cannot be used at any of these high temperatures. And this table shows estimated oxidation rates in mils per year or MPY, where the temperatures are shown in degrees Fahrenheit, from 1525 to 2075 degrees Fahrenheit. Increasing chromium, increasing temperature. And again, these alloys are the resistance alloys in these temperatures. Again, whenever data is missing, it means that the alloy has a high corrosion rate and is not durable at that temperature. Again, carbon steel, 1¼ chromium, 2¼ chromium, 5 chromium, 7 chromium, 9 chromium, and 12 chromium cannot be used at any of these high temperatures. This figure shows the results shown in the previous tables. Corrosion rate in MPY, temperature in degrees Fahrenheit, carbon steel, 9% chromium, 304 stainless steel, 800 H, 310 stainless steel. If you consider a corrosion rate of 10 MPY, the higher the chromium contents of the alloy, the higher the temperature it can withstand and still maintain a corrosion rate of 10 MPY. 800H HP alloy, 30 to 35 nickel, 19 to 23 chromium, 43 to 50 iron, carbon, aluminum, and titanium. 800H high performance is a nickel chromium iron alloy with significantly high creep rupture strength. The high strength results from close control of carbon, aluminum, and titanium contents in conjunction with a high temperature anneal. Affected units or equipment. Significant oxidation occurs in fired heaters, boilers, and other combustion equipment, as well as piping and equipment that operate in high temperature, oxygen-containing environments where metal temperature exceeds about 1000 degrees Fahrenheit. Appearance or morphology of damage. A. Carbon steel, low alloy steels, and 12 chromium stainless steels suffer general thinning due to oxidation. Usually, the component will be covered on the outside surface with an oxide scale, depending on the temperature and exposure time. Oxidation of a carbon steel nut on a stainless steel stud at 1300 degrees Fahrenheit. And this figure shows oxidation of a carbon steel grid from a sulfur reactor. And this figure shows oxidation of the other diameter of a carbon steel furnace transfer line. B. 300 series stainless steel and nickel alloys generally have a very thin dark scale unless exposed to extremely high temperatures where metal loss rates are excessive. This figure shows temporal evolution of oxide scale morphologies on model alloys nickel, chromium, niobium, molybdenum, and nickel, chromium, niobium, molybdenum, silicon during exposure in air 5% H2, 3% H2O at 900 degrees Celsius. Exposure time is 8 hours, 24 hours, 72 hours, and 168 hours. Prevention, mitigation of oxidation. A. Resistance to oxidation is best achieved by upgrading to a more resistant alloy. B. Chromium is the primary alloying element that affects resistance to oxidation. Other alloying elements, including silicon and aluminum, are effective, but their concentrations are limited due to adverse effects on mechanical properties. They are often used in special alloys for applications such as heater supports, burner tips, and components for combustion equipment. Inspection and monitoring of oxidation. A. Process conditions should be monitored to establish trends of high temperature equipment where oxidation can occur. B. Temperatures can be monitored with tube skin thermocouples and/or infrared thermography. C. Ultrasonic testing can be used to measure remaining thickness when oxidation occurs on the internal surface. D. Radiography testing can be used to measure remaining thickness when oxidation occurs on the external surface. Alternatively, the oxide could be removed, for example, using a flapper wheel to allow ultrasonic testing measurement of the remaining wall thickness. E. Electromagnetic acoustic transducer has been used to measure general external wall loss on heater tubes. Related mechanisms. 1. Other high-temperature gas corrosion mechanisms are sulfidation, high-temperature H2H2S corrosion, carburization, and metal dusting. 2. Oxidation damage referred to in this section is due to surface scaling. 3. Some damage mechanisms result in internal oxidation, which is discussed in another video. Challenge number 58. Additively manufactured nickel-based alloys are known to suffer from intergranular oxidation attack at 900 to 1000 degrees Celsius, which is the main reason for higher oxidation rates reported for additively manufactured alloys compared to their conventionally manufactured counterparts. Intergranular oxidation often occurs in the grain boundaries voids formed underneath oxide ridges. What is the effect of grain size on the intergranular oxidation attack in additively manufactured nickel-based alloys? Thank you for your time and attention.